Alright. So today, I'm going to look at test for divergence, p-series, and the integral test. First is test for divergence. And this is powerful, but very limited. And I say that because it's only going to tell you if something diverges. It will not help you in terms of convergence. And that's the most important part of this. Because eventually I have to test you guys on this stuff. And so at that point, right, you can use this, but only if a series diverges. So, or at least to prove that it diverges. It says that if we have some series, we take the sequence a sub n from the series, and we take the limit as n goes to infinity. If that limit does not exist, or the limit as n approaches infinity of a sub n is non-zero, then we can say that this thing diverges. In the case that we get 0, notice it says another test must be used. Or, in other words, this is inconclusive. And in big bold here, notice it says, if it equals 0, this does not mean convergent. Right? So, if we get 0, it's inconclusive. We get anything else, it diverges. So let's go ahead and take a look at a few of these. So it's asking us to use the divergence test to prove or to determine if these diverge or converge. So we want to take the limit as n approaches infinity of 2 over n squared plus 2n minus 3. So basically everything on the bottom is going to become infinite, right, if we tried to make a substitution. That ends up being 0. So if you forgot, numbers divided by infinity tend towards 0. Numbers divided by 0 tend towards infinity. So this gives us 0, which means inconclusive. Must do another test. Now we don't have one currently in our tool bag to do this, so we can't try another one here, but we do know that divergence test tells us nothing. So let's try the next one. We've got 2n squared plus 3n over the square root. So again, I need the limit. N approaches infinity. Now this time you might want to divide through by the highest power of n in the denominator. So if I do that, I'm dividing through by n squared. All right, I got the square root of n to the 4th. That's basically n squared. And then inside here, I'm dividing everything by n to the 4th. So by doing that, now everything here, or everything divided by n, right, when I take this limit, goes to 0. So I just get 2 out of that. Therefore, the series diverges. Right? It says as long as you get anything other than 0, then the test tells you it diverges. Good with those two? Okay. We've got 2 more here. This first one is a little easier to prove if we do a graph. So again, we still need to take, does the value 2 mean represent anything other than divergence? No. So recall I said that there are only so many of these that we can find the sum or where it converges to, that sort of thing. And this is not one of them. So just you got a number that tells you it diverges. That's it. All right, so I want to take this guy and take the limit as n approaches infinity of arc tan of n. So it might be beneficial then, as I said, to graph it if you're not sure how to find that limit. Well, the graph of arctan looks like this. And it's got 2 asymptotes. And those asymptotes are pi over 2 and minus pi over 2. So if I asked you, what does this function do as n approaches infinity? Well, it tends towards pi over 2. And if we get something that's non-zero, diverges. So typically I would give you D here to do. I'll go ahead and do it. So again, I need the limit as n approaches infinity, the nth root of 3. You can rewrite that as 3 to the 1 over n. So if you plug in infinity there, right, that's really 3 to the 1 over infinity. 1 over infinity is approximately 0. 3 to the 0 is 1. So this series also diverges. So not a ton to these so far. So the next test or particular series that we're going to learn is the P series. Okay. So here's the P series. So this is a series who has the form of 1 over n to a power p. And there are two situations that power p could be greater than 1, or it could be less than or equal to 1. If it's less than or equal to 1, it diverges, and if it's greater than 1, it converges. So one thing I would like to say here is do not confuse this with the geometric series. The geometric series, r had to be less than 1 for the absolute value. Here, p is greater than 1. There is a special p series, and that is when p is equal to 1. We call this the harmonic series. And I can guarantee you, somewhere down the line, a quiz or test, you will see this series. And this one's special because if we see it, there's nothing we have to do to prove. We can just say it diverges because it's been proven many, many times. No, you do not have to solve for where it converges. I'll be very specific if that is the case. So determine if each p series is convergent or divergent and justify your answer. Let's go ahead and do these guys. So remember, I need something that's 1 over n to a power. So this first one's real simple. I can just pull that 5/4 right outside the sum if I want. And I can do that because they have nothing to do with this index n. So I have the sum of 1 over n to the 15th. That is a p series where p is equal to 15. That number is obviously greater than 1, so converges. So now we got to do this for b. This one is pi times the sum from 1 to infinity, 1 over n to the 7/5. So that tells me p equals 7/5. That's also greater than 1. Converges. So those are real simple. What about C here? Well, this is just E. I can pull that out. But this isn't in the form of 1 over n to a power. I can write it that way. Right, I can rewrite this as 1 over n to the minus 0.4. Now, p in this case is minus 0.4, which is less than 1. Therefore, this diverges. Okay. Then what about D here? Any suggestions on how to start this one? So I need to separate the two sums, or at least break it into two fractions, yeah? Okay, so yeah, this is actually the 7th root, not 4 to the 7th. So I want to make this sum n equal 1 to infinity, 2n cubed over 4n to the 2/7 plus sum n equal 1 to infinity, 3n squared over 4n to the 2/7. So this is 1/2 sum. Now we've got n cubed over n to the 2/7. So I would subtract the powers. So this is going to be, what, 21 minus 2, so 19. And this one would be 3/4 sum n equal 1 to infinity. This is going to be n to the 12/7. But again, I need 1 over. Now it turns out in both of these cases, p is a negative number and it's less than 1. Therefore, this diverges. And if one of them diverges, then the whole original sum has to diverge. I don't even care about that one at that point. Technically, they both diverge. But if I show that one portion of it does, so Tom, did you have a question? Alright, so if I go on to this next one here, then notice that I've gotten, oh, sorry, C, sum 1 over n times n to the 1/2. You're asking about part C? Oh, maybe that was supposed to be E. Yeah, E, okay. So yeah, we got to write it as a summation first. So if we look at the terms here, this is the sum, and we've got 1 over, and this is n times square root of n, which is really n to the 3/2. Maybe I'll start here, right? If I want any term, it's n times square root of n. And that's n to the 3/2. So if we look here, we plug in 1. Every number here, 1, gives you back 1. If I plug in 2, I get that term. So it looks like we start at 1. And that looks like the proper form for that problem. So if that's the sum, P equals 3/2. That's greater than 1. This is convergent. So if you see a P series, then you can use that test. And all you have to do is just write it in the correct form, show what P equals, and then tell whether it converges or diverges. So again, not a lot of hard work to be done. Just got to get everything in the right form. All right. The next test is the only one that I feel is completely pertinent to Calc 2 because it's called the integral test, and we actually have to do integration. So this states that our function f has to be positive, continuous, and decreasing over the interval 1 to infinity, or there are some cases where we might not start at 1, we might start at 3 or 5 or something. Then we just call the sequence a sub n our function f of n, and instead of n we usually change to x when we integrate. So we're just going to take this function here, integrate it from the bounds that are given, and then if it says if the integral is convergent, the sum is convergent. So what does that mean? Well, that's saying that you get some number out of the integral. So you might get -10 or pi or -1,000,000. Then it says if the integral is divergent, then the sum is divergent. Well, how do you make an integral diverge? You get some kind of infinity out of it. So basically, if we get anything that's not infinity here, it's convergent. Now we've already done this one. This is a P series. We know that it converges. So it'll be nice to use the integral test instead to prove that it works. So the integral test says change the integral, or the sum, into an integral from 1 to infinity, 5 over 4 n to the 15. And instead of n, we're going to change to x. So we have a dx. A sub n is what we're taking as the function. Remember that an infinite sum, right, from 1 to infinity, can be taken and turned into an integral. And as a technicality, I'll do it this time and then I will refrain from the rest. This is an improper integral, so we would technically need a limit as x approaches infinity from 1 to c. Should make that c, sorry. And this would be 5 over 4x to the 15 dx. We could also take the 5/4 out to the front. So how do we integrate x to the 15? Well, we just rewrite it. And then it might be more familiar. So to integrate that function, we add 1 to the power and divide by that number. So we got to plug in 1 and c. So this is 5/4. Limit c approaches infinity. C to the minus 14 over minus 14 minus 1 to the minus 14 over minus 14. This guy right here is a number to a negative power. That means you could put it in the denominator. If I plug infinity in there, right, infinity in the denominator, makes this thing all go to 0. So I am just left with 5/4 times 1/14. So we get some number out of it. And that number tells us that this converges. Because it says if the integral converges, then so does the summation. All right. So now let's convert this one. All right, we want to do the integral test. So I'm going to do integral from 1 to infinity. 1 over x natural log x dx. Abood, are you asking why my answer isn't negative? The answer to that question is there's a negative there and a negative there. Okay. Regardless, if we get a negative number, that's okay. That would still be convergent. All right. So I want to do this integral. I said I'm going to refrain from writing it improper or with the limit out in front. So I'm going to let u equal natural log of x. Du then is naturally 1 over x dx. So this integral then is now 1 over u du. And we should know that to be the natural log. I left the bounds off because I don't want to convert them. So that's natural log of u from a to b. If we plug u back in, that's natural log of the natural log. And we need to evaluate from 1 to infinity. So this would be natural log of the natural log of infinity minus the natural log of the natural log of 1. This is infinity. And natural log of 1 is 0. Natural log of 0 is technically undefined. It's really heading towards negative infinity. So we get some combination of infinities. That tells us divergent. And even if you didn't know how to interpret this one you already know, right? The log of infinity is infinite. And that really means I don't care what the rest of the problem does, because it can't overcome or cancel out infinity. Are we all good with those? All right. Oh, sorry, one sec. Hopefully you didn't need the one I just erased. Do you have a question? Too late. Well, remember, I am recording these, so you can go back and check it if you need. But if you know what the question was, please, or feel free to ask. I don't mind answering it. So there's one more down here. And it's the sum n equal 1 to infinity n e to the n. So again, change it to an integral from 1 to infinity, x e to the x dx. That's by parts. Let u equal x, du is dx, dv is the leftovers, just e to the x dx. V is the integral of that, which is e to the x. So you get u times v minus the integral. This is evaluated from 1 to infinity. Minus the integral of v du. And of course we know that that's going to give us e to the x. All of this now from 1 to infinity. Now it's best first I guess let's just plug in. So I've got, and actually let me go back for this one, and let's go ahead and do the limit. I think it might help with the way you see it. Okay. So I just changed my infinities to c, and I'm now taking the limit everywhere. So let me plug in now. Then I would do minus, plug in 1. That would become plus e to the 1. So those last two there are going to cancel. And then I want to rewrite this as limit c approaches infinity e to the c times c minus 1. And I could have done this back here. Now the reason I do it that way is I don't know if you guys have done this limit before. If I try to direct substitute, I get infinity times infinity. That doesn't help us much. So instead, what I want you to think of is I've got two functions here that are battling out one another, right? And the question is, as c gets really large, what gets bigger faster? This equation here, which is a line, or an exponential? And the easy answer to that is the exponential. So whatever the exponential does, so does this entire equation. So if you take e to the infinity, you get infinity. So divergence. So I think I only have one more topic for you guys. So if there's no questions, I'll go ahead and move on to that. Do these need to be written with taking the limit? Yes, you should do it. Right? We talked about improper integrals before. The reason I don't do it sometimes is that in physics, we don't always write that out that way. Okay. So this next topic is getting a specific error for a sum. So the idea here is you have a sum that you know converges, and because it's an infinite sum, you can approximate it with an integral. You could take any integral and break it up into two integrals, or however many you like, as long as the function's continuous. So notice they took the integral here and split it up from 1 to n and from n to infinity. They then go on to say that they're going to let the 1 to n be the approximation that they want from the series. And therefore the n to the infinity, or n to infinity portion, is going to be called our error. So this is good if you are using a summation and you really only have to be accurate to so many decimal places. So then you can say, okay, I only need to take 10 terms instead of infinite amount of terms to get the thing that I want. So to do these, it says first show that the series is convergent using any method. So far that could be geometric, telescoping, integral, or p-series. And then it says Find out how many terms n are necessary to ensure that the sum of the series is accurate to the value given. And finally, use Excel and your response in part B to find the sum. So let's take a look at this guy. My mouse will move the page. All right. So first, I have to show that this converges. Well, this is pretty simple because this is a p-series. So p-series, p is equal to 5, which is greater than 1. Therefore, it converges. That's all we need to do to prove that it converges. That's part A. Find how many terms are necessary to ensure that the sum of the series is accurate. Okay? So, again, I'm going to translate that integral into the... translate the sum into an integral. And up there it told us our error was equal to the integral from n to infinity. And our function here is 1 over, I'm going to change it to x to the 5th dx. I'm also going to change this to a constant c and take the limit as c approaches infinity. Now, I want my error, it says accurate to 100,000th place. So the error in my sum has to be less than or equal to, so this is tens, hundreds, thousandths, 10,000ths, then I get to the 100,000ths place, but I'm going to go one more and put a 5. The reason for that is, if I'm trying to make it accurate to this place, a 5 in the next place tells me to round up. So whatever it tells you, go one more place, put a 5. So let's solve this integral now. So this is really x to the minus 5. And so if I integrate that, I get x to the minus 4 over minus 4. And I'm evaluating from n to c. Plugging those in. This is the limit as c approaches infinity. This, we can pull the minus 1/4 out in front. And rewrite it as 1 over. Right, it's x to the minus 4. So that's the same thing as 1 over. That's a c. So 1 over c to the 4th minus 1 over n to the 4th. So we take the limit here. If I approach infinity, 1 over infinity thankfully goes to 0. So all that's left here is negative 1/4 minus 1 over n to the 4th. So that's, or times that. So this is 1 over 4n to the 4th. That's the result of the integral, but all of that has to be less than or equal to this decimal. So now I just need to solve for n. So I think I had told some of you this trick before. I can just switch the end of the fourth with this guy instead of doing 2 steps. So let me see what that number is. That is 50,000. So that says end of the fourth is greater than or equal to 50,000. So take the fourth root of both sides. So n greater than or equal to, and that comes out as, I have here, 14.95, or approximately 15. So that's telling me if I want the integral to be, the sum to be accurate to the 100,000th place, then I need to get 15 terms approximately. Now when we do it on Excel, I think it's going to show us that it's around 14. So it actually looks like you can round down. But let's go ahead and do that. So let me pull up Excel. Let's see if we can't figure this guy out. Alright, I guess we'll just start here in the E, since it's the first one on the board. Okay, so my terms start at 1, and they go up to some number. So let's take that. Oops, come on. Okay. And I want to drag that guy just to get a bunch of terms. Didn't need 110, but we got 110. Okay. Now I want to put my summation in here. So this equals the, let's see, it'd be 1 divided by this term, oops, to the 4th power. Just to be safe, I'm going to put some parentheses around it. Okay, so now let me drag that. So notice we've got a bunch of values now. And then I want to start calculating the running sum. So this equals sum. And it would just be 1 term at that point. And the first 2. Now does somebody recall, I think if I pick the first value and then hit F4, it's not working. So I think I need dollar signs here to make this do the running sum. Let's see if I can make this work. Oops. There we go. Let me do that one with this one as well. I think it will then keep the first term every time and then add every subsequent term. Pretty sure this will work. Unless I'm forgetting something here. So let me take these two and drag and see if it seems to work or not. So yeah, it's starting at the first term and then calculating up to the 8th, so that's good. Alright, so that's our sum that we want. Now let me drag this for a little while, and then let me space this out so we can see more digits. And then I'll go ahead and erase the board so you can actually see them all. All right. So what do I have here? Well, I've taken my n values, right? 1 to what? Excuse me. I've then plugged them into 1 over n to the 4th. And then over here I've calculated the sum. So this is the sum of the first term, this is the sum of the first 2, sum of the first 3, and so on. We were trying to be accurate to the 5th decimal place. So 1, 2, 3, 4, 5. So this one, that one, is that mark showing up on there? Not really, right? Darn green marker. So 5th decimal place, 5th. Alright, so they're still changing. Now we said that we should have the sum be accurate to the 5th decimal place after, what was it? 15 terms? Is that right? Tens, hundreds, thousands, 10,000, 100,000s, yeah. So these should be the same from then on. Looks like it's a little off. So the question is, did my sum calculate properly? Let me check that again. So let's see. I thought I checked it and it said that the sums were calculating properly. So it should be 1 through 4. This one should be 1 through 9. So at the 15th term, that's where that term they should be repeating. Let me do a couple more. This happens to me every time when I do something silly. Let me just... So again, if you look here, notice that as the sum is accumulating, we start with 0.03, then 0.035, 0.036. That 6 continues on. The next digit grows to a 9 and continues. Then the fourth digit starts as a 1 here, then a 2, and then it looks like it continues as a 2. So if I were to scroll down and even calculate more terms, right, it should be 1.03692 forever. Right, 1.03692. So, the whole point of the problem that we did was that the first time we see that technically is at 13 terms, but it repeats for the first time at 14 terms. So we need no more than the first 14 terms to make the sum accurate to 5 decimal places, because from then on, I've calculated all the way up through 105, and it's still accurate to 5 decimal places. So what did you guys say here? Can you post the Excel function for these summations? The camera cuts the function off. Yeah, it's the same function that was given in the problem. So, right, I can double click here and you can still see the function. It's 1 over the number n to the 5th. And column G is just the running sum. So it's the sum of the first value, then it's a colon to the last value, and the first one you just have to put a $ before the letter and a $ before the number. And that gives you the running sum starting with this point and always this point and then adding up to wherever you're at. But yeah, I can put this up for you guys, I suppose. So I think we have one more example to do, which is this one. And again, typically if we were in class, I would have you guys do this one. All right, so first I need to prove that this is convergent. This is not a p-series, geometric. It'd be kind of difficult, I think, maybe to do the decomposition to try and prove that it's telescoping, because we've got that log part. And the test for divergence is no good because it doesn't prove convergence. So the only thing we can do is do the integral. So we have to do the integral test here. So limit c approaches infinity, integral 1 to c, 1 over x log x quantity squared dx. Now the nice thing is I've already done a problem close to this, and once we integrate it the first time, we already know what the solution looks like, so we don't have to integrate it again for the error. So right now we're just trying to prove, does it converge? So I've got this. So I'm going to let u equal log. du is going to be 1 over x dx. So this is limit. C approaches infinity. This is now going to be du over u squared, or u to the minus 2 du. So integrate that. That's going to be u to the minus 1 divided by minus 1, or minus 1 over u. From some a to b, I guess. And then if we replace, u is natural log of x, and that's from 1 to c. So let's plug those in. So this is limit, c approaches infinity, negative 1 over log c minus, or now it's going to be plus 1 over log 1. So if I plug infinity in here, one divided by infinity is what? That's going to go to 0, right? And then 1 over log 1, well, that causes a little bit of trouble, doesn't it? Because log of 1 is 0. This whole thing's going to be infinity. Well, if I can't show it converges, then I can't go any further. So that I wanted to do that to give you an idea of when it doesn't work. We could simply come over here and say, let's start at 2. So if I do that, got log 2 now. And so this wouldn't be infinity, it'd be whatever 1 over log 2 is. Which would be some number. If the integral gives you some number, it then converges. Alright, so let's go ahead and finish this out. So I need the integral from n to infinity, or in this case, let's change this to c again. So we have limit, c approaches infinity, n to c, plugging in x has to be less than or equal to, right? I'm writing my error equation. Now it says accurate to the ones place. So I go one more and put a 5. Okay. Now we've already done this integral. We know exactly what it does. It turns out to be 1 over the natural log of whatever this value is. That's why I said it's nice that this one had to be proved that way. All right, because just like that one, the limit is going to cause that first piece to go to 0 again. Again, I can swap these guys. One divided by a half is 2. And to get rid of that log, I got to take e. So I get n equals e squared, or greater than or equal to e squared. So that's not a whole number, that's 2.7 squared, which is 7.29. So it's saying if we started at 2, we should need approximately 7 terms. So again, let's go ahead and Excel this guy. Let me get rid of this side of the board so we can see the Excel. Any questions about this before I erase it? Should it be minus 1 over log n? So remember that it's negative here, but then the second term gets subtracted, so it becomes plus. Anything else? All right. So like I said, let me just do some Excel work here and see what we get. Now, I haven't done this one in a while, so, and plus I had to adjust it to make it work even. So let's cross our fingers that Excel tells us the right things. So let me open up a new page here. Where's the workbook? Oh, it's way over here. I can't see it. There we go. Come on, mouse. Alright, so a new sheet. Again, I want first column here is going to be n. It says we only need 7. Let's go to maybe 15. This column is going to be our function, which is 1 over n times natural log of n. So this equals 1 divided by, in parentheses, this number times, and I think, yeah, it recognizes ln, okay, of this number. Now see, that's why we couldn't start at 1 before, because it's not within the domain. So now if I take this down here, if it'll fix it. Nope. Let's make this I3. Okay. So let's see. Now we wanted set accuracy to what? The ones place? But it looks like, alright, so now we need the sum over here. So equals the sum. This one will just be of this term. Then we need the sum of this one, but this time I need to put the dollar signs in. So 1 before the letter, 1 after. Then we need a colon to the point that we want to get to, which is this one. Okay. So let's see if it just does it with 1. It's smart enough to pick it up. Yeah, I do need n squared. Keep doing that. I keep putting the wrong thing in. So yeah, log of this guy squared. There we go. Run this again. Okay. Let's make sure these worked. Come on. I4 times log of I4 squared. I5 times log of I5 squared. Okay. And then this is the sum of the first 3 terms. And this one should be the sum of the first 8. Okay, or first 7, I guess it is. So it looks like from the beginning it's 1. So it doesn't seem that we really need 7 points. Oh, it did not like that. So it looks like this problem is weird because these don't seem to change. So let me think about this one some more.